All right, moving on to 9.4. 9.4 is all about convergence tests. Basically, we're going to look at some more general ways to determine if a series converges or diverges without necessarily knowing that it's a geometric series or a telescoping series or whatever. And at this point in the chapter, we really aren't focused so much on finding what the sum is. We just want to know if it converges or diverges. So we're going to start to build up a bunch of convergence tests for the next, I think, 3 sections. We're going to talk about a whole bunch of different kinds of convergence tests for determining if a series converges or diverges. So the first thing that we should go over is what's called the divergence test, which is kind of funny because the section's called convergence tests, and the first theorem we cover is the divergence test. But here's what the divergence test says. It says if you take the limit as k goes to infinity of the terms of a sequence and you get something other than 0, then you can be sure that the series diverges. I may have misspoken there a second ago. It's the terms of the series, right? So if you take the limit of these terms and you get something other than 0, then the series diverges. Now, something to be careful about here is that the logic only flows in one direction. So in other words, if you take the limit and you get 0, that doesn't necessarily mean that the series converges. It just means the series might converge, but it also might diverge. However, if you take the limit and you get something different from 0, then you can be certain that the series diverges, right? So that's what this theorem is saying. So just because you get 0 when you take the limit doesn't mean the series converges. And we've already seen examples of, for example, the harmonic series, right? 1 over k. The limit as k goes to infinity is 0, but we saw in the previous section that that series diverges still, right? So just be careful. The logic only flows in one direction here. So if the limit is something other than 0, then the series definitely diverges. If the limit equals 0, then maybe it converges, maybe it diverges. We don't really know. Okay? The test is inconclusive. Another thing that I'll point out, because I know that this is maybe a little bit confusing, but UK here represents just an individual term of a series. It's not an nth partial sum. Okay, and that's important to kind of to realize, because in the previous section in 9.3 we were talking about how if the sequence of partial sums converges, then the series converges, right? And that's true if you're talking about a sequence of partial sums. But we're not talking about a sequence of partial sums. We're just talking about the individual terms of the series itself, right? And again, right, it's possible for that sequence to converge, but the series could still diverge, right? Because you're not talking about the partial sums, you're just talking about an individual term. Another way to say this, and I think I've probably mentioned this already, but another way to say this is that if the series converges, then you know that its limit then you know that the limit of the individual terms has to go to 0, right? So that's another way of saying the same thing here. Okay. Again, the logic only flows in one direction, though. So it's not necessarily the case that just because the limit is 0 that the series will converge. Okay. So to give you an example of this, let's show that this series here, k over k plus 1, diverges. So we've got this series, k over k plus 1. And we'll use the divergence test to show that this thing diverges, right? So if we just take the limit as k goes to infinity of k over k plus 1, we get 1, right? And that's not equal to 0. So the series k over k plus 1 diverges. Right? It's that simple. Okay, so that's all there is to that. Right, so the divergence test is pretty easy. Again, if you take the limit and you get 0, that doesn't mean that the series converges. It could converge, but it could also diverge, right? So this test is really only good to show that a series diverges. It doesn't show that a series converges. Okay, here's another important fact about series, okay? If you have two series, UK and VK, and they both converge, then their sum will converge and their difference will converge. And not only that, but you can distribute the summation, right? So the sum of UK plus VK is the sum of UK plus the sum of VK. And the sum of UK minus VK is the sum of UK minus the sum of VK, right? If UK converges, then C times U sub k, then the series C times U sub k is also going to converge for any real number C. So this is true for any real number C. And in that case, you can pull that constant out of the summand, right? You can pull that constant out of the summand. That's what that's called. Okay. Now, if on the other hand the sum of UK diverges, then the sum of C times U sub k is also going to diverge, unless C happens to be 0, and then I'd have to think about what happens in that case. It probably, if C is 0, then for sure this thing is going to converge, right? It's just going to converge to 0. So never mind. I don't have to think about it. I know that it's going to converge in that case. Okay. And then the last part of this theorem is that convergence or divergence is unaffected by deleting a finite number of terms from a series. And so in particular, you could take the first 5 or 6 terms out of a series, and if the original series converges, then the one with the deleted terms also converges. If the original series diverges, then the series with the deleted terms also diverges. Okay? Now, something to point out about that, though, is that while the convergence is not affected, the sum is affected. And we saw that when we were looking at geometric series in the previous section, right? So we saw a geometric series where we started the index at 2 instead of at 0. And in order to find the correct sum, we had to delete the first 2 terms from it, right? We had to subtract the first 2 terms from the one that started at 2 instead of starting at 0. So the sum is affected, but whether or not the series converges or diverges is not affected when you delete a finite number of terms from the series. So let's practice applying these facts. By the way, this is theorem 9.4.3, and I just point that out because in your homework you'll have a couple problems that say use theorem 9.4.3 to prove blah blah blah, and this is the theorem that they're referring to. But let's do this. So example 2 here, we want to find the sum of this series. So let's find the sum of this series. So I guess since it has a sum, it converges, right? So we're already being told that it converges. Let's find its sum. So the sum is sum from k equals 1 to infinity, or the series rather is the sum from k equals 1 to infinity of 3 over 4 to the k minus 2 over 5 to the k minus 1. Okay, so if I want to find the sum, well, I'm going to use theorem 9.4.3 part A, which says that I can distribute that summation, right? So this is going to be the sum from k equals 1 to infinity of 3 over 4 to the k minus the sum from k equals 1 to infinity of 2 over 5 to the k minus 1. And then here I can remove the 3, right? So I'm going to use part B of that same theorem to remove the 3. And then that's going to become a 1/4 to the k, right? So if I remove the 3, then I have 1/4 to the k. That's the same thing as 1/4 to the k. And then I'll do the same trick here. Take the 2 out. And then I've got 1/5 to the k minus 1. Now these are both geometric series, okay? And the first term of this series is going to be 1/4, times 3, so 3/4. So this is going to be 3/4 a over 1 minus r, right? And for this one, first term of the series is 1/5 to the 0, okay, which would be 1, times 2. So first term is 2, so it's going to be a over 1 minus r. Okay, 1 minus 1/4 is 3/4, and 3/4 divided by 3/4 is 1. 1 minus 1/5 is 4/5. 2 divided by 4/5 is 2 times 5/4, that's 10/4, or 5/2, right? Is that right? 4/5. You flip and multiply. 5 times 2 is 10. 10/4 is 5/2. Yep, okay. All right, double check my arithmetic, but I think that's right. Okay, and then 1 minus 5/2. That's 2/2 minus 5/2, so that's -3/2. Okay, so we get a negative value there, because this one is a bigger sum than that, I suppose. Okay. Very good. Here's another example of using theorem 9.4.3. It says determine whether the following series converge or diverge. And we'll do this for 5 over k and then 1 over k. Oh, but this one starts the index at 10, so let's be careful there. So this time we're not so interested in finding the sum. We just want to know if the thing converges or diverges. So we've got the sum from k equals 1 to infinity of 5 over k. Okay, well, this is going to be 5 times the sum from k equals 1 to infinity of 1 over k. I already know that 1 over k diverges. Okay, so 1 over k, the sum from k equals 1 to infinity of 1 over k diverges. So 5 times a divergent series is still going to be a divergent series, right? So this, so we'll say since 1 over k diverges, five times the sum from k equals 1 to infinity of 1 over k also diverges. Okay, so task completed. Okay, next one. Oh, sorry. So the answer is just that it diverges. Anyway, so next one, we've got the sum from k equals 10 to infinity of 1 over k. Well, notice that this is just the sum. So we'll say this equals the sum from k equals 1 to infinity of 1 over k, except that you're missing the first 10 terms. So I suppose we could write that like this, k equals 1 to 10 of 1 over k. And so we've taken a divergent series and we've removed a finite number of terms from the series. But when you remove a finite number of terms, that doesn't change, right? This is by theorem 9.4.3 part C. It doesn't affect, right? Convergence or divergence is unaffected by deleting a finite number of terms. So we'll say since, again, right? And we know this thing diverges. It's the harmonic series. We showed that it diverges in the previous section. So since this diverges, by theorem 9.4.3 part C, this thing also diverges. Okay. Very good. Okay, so we've talked about the divergence test, and we've talked about this useful fact about kind of the algebra of series. You know, you can split sums and differences. You can take out constants, right? And you can delete finitely many terms without affecting the convergence or divergence of the series. So the next test that we'll talk about is called the integral test, and this is something that we have some experience with, actually. But the integral test says this. So let's say that the sum of u sub k is a series with positive terms, right? So all the terms are positive. If f is a function that is decreasing and continuous on this interval from a to infinity, and if u sub k equals f of k for all k greater than or equal to a, then the sum uk and the integral f of x both converge or both diverge. Okay, so they converge or diverge together. So if you want to show that an integral converges, you could show that the series converges. Or if you want to show that a series converges, you can show that the integral converges or diverges, right? But the conditions are the series has to have positive terms and the function that matches the terms of the series has to be a decreasing function and continuous. All right. So let's prove some stuff using the integral test. So example 4 here says, show that the integral test applies, and then use the integral test to determine whether the following series converge or diverge. And we'll do this with the harmonic series, which we already know diverges. And then we'll do it with this other series, 1 over k squared, and see what happens there. All right, so we've got sum from k equals 1 to infinity of 1 over k. And we're supposed to, first of all, show that the integral test applies, and then second of all, perform the integral test to determine if the thing converges or diverges. So, what conditions have to be met in order for the integral test to apply? Well, the terms all have to be positive, and then the terms have to be decreasing, okay, and continuous. So, so here's what we'll say. So note that 1 over k is positive for all k, for all natural numbers k. And then also note that f of x equals 1 over x is decreasing and continuous on the interval from 1 to infinity. Okay, so those are the conditions, right? So we can say, therefore, the integral test applies. Okay, now to show that this thing, well, we already know it diverges, so I'm just going to say to show that it diverges, we just have to show that the integral diverges. So let's take a look, right? So the integral from 1 to infinity of 1 over x dx, well, it's an improper integral, right? Because you've got that infinity. So we're going to say this is the limit. Maybe I shouldn't use k So maybe we'll say limit as a approaches positive infinity of the integral from 1 to a of 1 over x dx. That's going to be the limit as a approaches positive infinity of ln of x from 1 to a. And that's limit as a approaches infinity of ln of a minus ln of 1. ln of 1 is just 0, right? And ln of a goes to infinity. So this goes to positive infinity. So it diverges, right? So we can say since the integral diverges, the series also diverges. Okay, so that's that one. And now let's do the same thing for the sum from k equals 1 to infinity of 1 over k squared. So first of all, we have to show that the integral test applies. So we have to show that all the terms are positive. Well, yeah. So note that 1 over k squared is definitely positive for all k. By the way, I mean, so 1 over k, if k is like -2, then obviously this is not positive, right? But here I'm saying for all k, where k is a natural number, so it's a positive whole number, right? So if k is a positive whole number, then this is definitely positive. And same thing here, right? If k is a positive whole number, this is definitely positive. So for all k. And then note that f of x equals 1 over x squared is decreasing and continuous on the interval from 1 to infinity. So the integral test applies, okay? And so to perform the integral test, we would integrate. Again, this is an improper integral, so we'll take the limit. Okay, so that's going to be a negative 1 over x. Whoop, I forgot the limit. Let me write the limit. Of, we'll say, negative 1 over x from 1 to a. And that's going to equal limit as a goes to infinity of negative 1 over a minus negative 1 over 1. Now, as a goes to infinity, this thing goes to 0. So you just get 1, right? And so we'll say, since this integral converges, the series also converges. Now, one thing that's maybe a little confusing is that you might think, well, this integral converges specifically, it converges to 1, and so the series must also converge to 1. But that's not necessarily true, okay? In fact, I think this series converges to something weird, like pi squared over 6, or something like that, okay? Because here you can kind of think of this like you're taking a sum, but the sum is like it's the sum over all the real numbers. Here you're just taking the sum over all of the whole numbers, right? And so you're not going to quite get the same thing, is what I'm trying to say, right? It's not quite the same. So that's that. I'm going to pause the video so I can tell my kids to turn down the music. Crazy kids. All right. Okay, so that's that for the integral test. So now we're going to look at another kind of series that comes up really often. And in fact, both of these series were examples of this kind of series, and it's a p-series, right? So a p-series is an infinite series of the form 1 over k to the p. So yeah, both of these series are examples of p-series, but so would something like 1 over the square root of k, because you can rewrite that as 1 over k to the 1/2 power, so p would just be 1/2 in that case, right? So this is also a p-series. And then just so that we're perfectly clear, 1 over k squared is a p-series. 1 over 2 to the k is not a p-series. This is a geometric series, right? So just be careful about where the exponent is. Okay? If the thing that's changing is in the exponent, then it's geometric, right? If the thing that's changing is the base, then it's a p-series. Okay? But we have kind of a similar result for p-series as we did for geometric series. In a way, it's sort of like the opposite of geometric series. But anyway, so the series 1 over k to the p converges if p is greater than 1, and it diverges if p is between 0 and 1. You can prove this using the integral test, and in fact, we've already done that. Back in 7.8, we proved this. I think it was like the second or third example we looked at in 7.8. Yeah, we proved that this is the case, right? That this thing is going to converge. We proved it using the integral test. So really what we were doing is we were taking integrals of 1 over x to the p, and we said, for what values of p does this thing converge or diverge? And then we proved that, if p is greater than 1, it converges. If p is less than 1, then it diverges, right? Anyway, so with that in mind, let's look at a few series and determine whether they converge or diverge. So the first one is sum from k equals 1 to infinity of 1 over cube root of k. Okay, well, so that's a p-series, right? This is sum from k equals 1 to infinity of 1 over k to the 1/3 power, right? Cube root of k is the same thing as k to the 1/3 power. So this is going to diverge. It diverges because it's a p-series with p equals 1/3, which is less than 1. Okay? What about our favorite series, the harmonic series? Well, we already know it diverges, and we've shown it 2 different ways. We showed it at the end of 9.3, and then we just showed it using the integral test a second ago. But notice that it's a p-series, right? So I'll say this thing diverges, right? Because it's a p-series with p equals to 1. With p equals 1, right? So I guess I should say less than or equal to, right? Which is less than or equal to 1. Because as long as p is less than or equal to 1, the series is going to diverge. Okay? Okay, what about sum from k equals 1 to infinity of our next favorite one, 1 over k squared, which we've already proved converges. We've proved that in the previous exercise. We proved that it converges. Well, so this one, we can see now with the p-series test that this converges for sure, because it's a p-series with p equals 2, and that's greater than 1, right? So it converges by the p-series test. So the p-series test is pretty easy and pretty nice. And that's that. That's all I have to say for this section.